Hi, welcome to QBites, your bite-sized pieces of quantum computing. My name is Rene from Valorem Reply, and today we're going to talk about the Quantum Intermediate Representation QIR. And for this, I'm honored to have a special expert guest today, Cassandra Granade. Hi, Cassandra, and welcome to the show. How are you today?
I'm doing well, thanks. Thanks for having me.
Well, thanks for coming back for recording another episode. So this is very much appreciated. But for the folks that might have missed your previous episodes, where have you been a guest? Can you tell us a little bit about yourself and your background as it relates to quantum computing, computer science, all the related things?
Absolutely. Yeah, no. So I did an undergraduate in physics, CS, mathematics, couldn't really make up my mind, heard about this new exciting quantum computing thing. Went on from there to do a PhD, and then joined Microsoft, working on the quantum team a little under 5 years ago now, and have been working on Q Sharp and the quantum development kit since, and really happy with all the amazing things we're able to do there. Um, and I see you have a copy of the book that recently put out, available from Manning Publications, on learning quantum computing with Python and Q Sharp.
Exactly. This is the book, folks. If you did not get a copy, get a copy. It's with Cassandra and as well as Sarah Kaiser, the authors of the book. And it's really nice because it's written in such an approachable manner, right? And so you don't need to have a PhD in physics. And so that's me, for example. I'm a computer scientist, right? So like this is perfect. Um, but yeah, thank you, Cassandra, for the introduction. And we in the previous episode, like I said, we actually talked about your work on the Azure Quantum team or the Quantum Development Kit and so on, especially on noisy quantum systems, right? And that it's so important that we're also able to simulate good noise, right? Noise that is realistic to what an actual quantum computer would produce. Is there any news since we talked the last time regarding that? Of course, the noisy quantum system, but also the broader level. The QDK and Q sharp, and maybe you can actually just again for being inclusive here, for making sure everyone's on the same page. Just explain us a little bit all about it.
Absolutely. So let me take that last piece first, then.
Yes.
Because I think you really touched on something really important there, which is if I go and run a quantum program on hardware today, noise is a part of reality. I have to understand the impact that noise has on how I run those programs and what outputs I get from them. And if I look at what's happened over the past few years, and especially over the past few months, that noise has gotten impressively good. The lower and lower levels of noise. We see new and exciting announcements about that. Um, but it's still where we're at today. And so being able to simulate the impact of that noise has on quantum programs that we run, that's really an important part of that kind of quantum development workflow, to be able to understand here's how that will impact what answers I get out, how I can go use them as part of a broader application that uses uh, eh, quantum computing. So to that extent, as you say, we talked about on the last episode that I joined about the open system simulator. That's or noisy simulator, that was released as part of the quantum development kit recently. And, I think it's been really exciting to see the feedback about that, to hear how that's really enabling people to do new and interesting things, and really address that kind of workflow. I think there's also some really other kind of exciting things in terms of community that have happened around that as well. One that surprised me a little bit, but has been really neat to see. We chose to implement that simulator in Rust.
Really?
And, that's turned out to be a really neat choice for us, and something that we've gone on and, developed other components in Rust and things like that as well. And I think that's something that has been really neat to see, kind of people engage with that and respond to, and
Mhm.
kind of watching the growth of that community as well.
So let's talk about Q Sharp, which is another interesting language, because developers can actually write and implement quantum logic in Q Sharp directly, and this will also be. like in Q Sharp, you can also leverage an SDK called the QDK, the Quantum Development Kit, right? And so this can run on simulators, but this, of course, in the end, you want to run it on real hardware, on real quantum computers. And every quantum computer is, of course, a little bit different. And even from the same vendor, it might have the kind of different instruction sets, right? If it's a new updated model or so, there's constant changes because we're on this rapid growing kind of field at the moment. And so there is definitely a need for having this kind of more stable intermediate layer where you can basically translate your high level language like Q Sharp, Python, Rust, whatever, and then put this into an intermediate representation, which is then basically more generic. But anyhow, let's talk about this kind of QIR, the quantum intermediate representation. Is it similar to .NET? For all the .NET developers that know .NET and the CIL, the Common Intermediate Language, which is also a similar kind of model. So is the quantum intermediate representation QIR, is it similar? Is it comparable? Or did I just tell bullshit?
I think that's a good comparison to make. I think what I'd really highlight there is the QIR, the Quantum Intermediate Representation, is it's similar to .NET IL, but it's based on LLVM IR, and so really kind of comes out of that history fairly strongly. And there, if I kind of look at some of the history of classical compilers, I might have a high level language, and then I might write some optimization passes for it. But then if somebody thinks of a new pass, or they think of a new way that they want to generate code or target some other device with,
Mhm.
then I have to now go back and kind of couple that all the way up through the high level language. But where LLVM has really changed that landscape classically has been if I have a new high level language, or if I have a new optimization pass, or a new kind of device, or even not a device at all, something like we see LLVM output targeting WebAssembly or things like that, which are, fairly outside of kind of the execution model of where a lot of high level languages kind of started.
Right.
Um, so LLVMIR really supports that by allowing communication between different parts of the stack, even when they weren't necessarily explicitly designed with each other in mind. And it's, that kind of decoupling and modularity that really enables that interoperability. And I think those are the lessons we've really tried to learn in the quantum community more generally, and why I'm really excited to see the QIR Alliance take off and some of the amazing things that they've been able to do. I absolutely agree with what you're saying about, there some of those challenges of there isn't exactly a single instruction set, like even something like x86 or ARM, where we know that's going to be pretty much the instruction set moving forward. But it's even more than that, like capabilities like having classical control flow and intermediate measurements and things like that. We need a way to be able to represent those in an interoperable way. And that's where we get into needing, we could try and do a lot of that. Or we could go look at the history of how that's done in classical computing. And I think it's really that latter approach that we see taken by the QIR Alliance with quantum intermediate representation and reusing a lot of the infrastructure offered by LLVM.
Gotcha. So the good part, it's basically also, well, this is not only the good part, but what I'm trying to say is basically since it's based on LLVM, it's actually also part of an open source kind of framework, right? So this is actually really nice. And you mentioned like already the QIR Alliance, right? So this is
Mhm.
what is it actually? Tell us a little bit about it, and what is the goal actually of the QIR Alliance? What are they trying to achieve here? With, of course, like we understood, like we need this kind of intermediate representation, and so is the QIR Alliance trying to um, kind of lobby for it with multiple vendors, or what is the QIR Alliance actually going to do?
Uh, so first and foremost, I definitely recommend checking out the website, qir-alliance.org. That'll take you to kind of an outline in more detail, as well as some of the ongoing open source projects at QIR Alliance. But I think what I'd really, highlight here is it's a joint effort. That an intermediate representation that's supported by one tool or one product or one service isn't you know that's not going to get us to where we need to that fully interoperable role that we just talked about. So it's really, I think, neat to see see the joint effort out of the QIR alliance, including Microsoft, including different hardware vendors, QCI, Quantinuum,
Hmm.
um, and Rigetti, and research groups, Oak Ridge National Labs. So we see a lot of really kind of joint investment and effort there in getting us to that fully interoperable world. Um, that's really necessary to deliver on, I think, really a lot of the exciting potential of quantum computing.
Gotcha. And so the QR Alliance is this kind of joint effort to develop this forward-looking quantum intermediate representation with a bunch of partners. And you mentioned Rust before, so I guess also Rust is part of that somehow.
Well, yeah. So, I mean, one of the projects out of the QIR lines that I'm personally really excited to see is PyQIR. So that's a Python package, or rather, set of Python packages for loading and parsing QIR in your Python project, for working emitting QIR from your Python project,
Hmm.
and start it, to try and help bridge from kind of it's there's a lot of investment and infrastructure in the Python ecosystem. That's
Sure.
part of why we chose to highlight Python in our book. It's why there's Python interoperability as part of the quantum development kit, and it's why we see a lot of other tools written in Python. So being able to reach out to that is really important. And the PyQIR packages really make it possible to work with at least some parts of QIR, and in some ways from where that ecosystem is.
Gotcha.
Where that one, where why I mentioned Rust in that is trying to work directly with LLVM from Python is kind of a pain. That but on the other hand, there's this really, really neat project called Pi03 that is a Rust library to help you write Python libraries in Rust.
I
And
love it.
that's what the QIR Alliance used to go write PyQIR. And you can go check out the GitHub repository for it and see how really that's been an incredibly useful tool for making QIR available to the Python world
Yeah.
using Rust. I mean, as a user of that package, you may not know, or, it's not something you immediately need to care about that it's written in Rust. But kind of underneath that sort of API, if you go, look into the repository, it's that's one of the things that really has enabled that. And I think it comes full circle in that's Rust is itself built on LLVM,
Hmm.
so it's one of those that allows for this kind of surprising retargeting, and I think it's really kind of part of that story as well.
Nice. It's actually, this is how you truly engineer things, right? You use the right tools for the right job, and basically, hey, why not use it if it makes your life easier, and you get a more cleaner and nicer, maintainable code base and whatnot, right? There's a lot of benefits here. Building on top of existing stuff, right? I mean, this is the right way to go. So totally makes sense. Thanks for explaining it.
Yeah, no, thank you for the question.
Well, we're already at the end of the show here. We could talk for much more hours about the QIR and the QIR Alliance and all the amazing stuff with all the different programming languages. And you definitely notice, I think, like this is the beginnings. We're still in the beginning of like, broad adoption of quantum computing. So thank you so much, Cassandra, for being here with us again and sharing your insights. That is very much appreciated.
Absolutely, and thank you for having me. It's really great to have the opportunity to talk with you and share some of the exciting things that have been happening.
Awesome. Well, and thanks everyone for joining us for yet another episode of QBites, your bite-sized piece of quantum computing. Um, Watch our blog, follow our social media channels everywhere, basically, where you can hear about all the upcoming episodes. And of course, on our websites, you can find all the previous episodes from season 1 till season 5 now. And this also includes Cassandra and a few other of her colleagues from the QDK team, like Bettina and a few other folks. Of course, I'm not mentioning all of them because you got to watch these episodes to learn all of it. Well, thanks, everyone. Take care, stay safe, and see you soon. Bye bye.